composite column refers to a structural element used in architecture and engineering that is made by combining two or more materials to optimize strength, durability, cost, or functionality. These columns are particularly common in modern construction, where hybrid solutions are often more efficient than using a single material alone. Types of composite columns. Concrete-filled steel tube, CFST columns. A steel tube is filled with concrete, combining the tensile strength of steel with the compressive strength of concrete. Benefits: high load-bearing capacity, good fire resistance, and reduced cross-sectional size for the same strength. Encased steel columns. A steel section, like an I-beam, is encased in concrete. The concrete protects the steel from corrosion and fire, while the steel improves tensile capacity. Reinforced concrete columns with embedded steel sections. Combines traditional reinforced concrete with a centrally embedded steel profile. Enhances load capacity and ductility, especially useful in seismic zones. Timber steel composite columns, less common but gaining popularity in sustainable architecture. A wooden core or outer frame is reinforced with internal or external steel plates. Offers a balance of aesthetics, environmental benefits, and structural performance. Advantages of composite columns. Improved structural performance. Each material complements the weaknesses of the other, resulting in superior strength and ductility. Space efficiency. Smaller cross-sectional area needed compared to pure concrete columns. Fire and corrosion resistance. Concrete protects internal steel, and additives or coatings can further enhance durability. Ease of construction. Prefabricated components can speed up site assembly. Applications. Composite columns are used in high-rise buildings to handle high axial loads, bridges where load and environmental conditions vary, industrial structures, seismic retrofitting of older buildings, design considerations, load-bearing capacity, buckling resistance, fire performance, connection detailing between composite and surrounding elements, differential material behavior like thermal expansion and shrinkage, codes and standards such as ASC, American Institute of Steel Construction, and Eurocode for provide detailed guidelines for designing composite columns. Conclusion. Composite columns represent a smart fusion of engineering materials to meet complex architectural demands. By combining the best properties of different materials, they offer superior strength, efficiency, and flexibility, making them a mainstay in modern structural design. Brick or masonry columns are structural and architectural elements constructed using bricks, concrete blocks, or stone. These columns serve both functional and aesthetic purposes in residential, commercial, and institutional buildings. They can support loads from above, such as beams or arches, and also enhance the visual appeal of a structure. Types of masonry columns. Solid brick columns. Built entirely from bricks and mortar, these columns are common in traditional and historical architecture. They provide solid support and can be either load-bearing or decorative. Reinforced masonry columns. These include steel reinforcement, rebar, and are filled with grout or concrete to improve strength, making them suitable for seismic zones and heavy load-bearing applications. Hollow concrete block columns. Made with concrete masonry units, CMUs, these columns are often used in modern construction due to ease of installation and cost-effectiveness. Like brick columns, they can be reinforced. Stone columns. Constructed using natural or cut stone, these columns offer a high-end, durable, and traditional look. They are often used in monumental architecture. Functions of masonry columns. Structural support. They carry vertical loads from slabs, beams, or arches and transfer them to the foundation. Aesthetic design. Often used to add elegance or historical style to facades, porches, or gateways. Partitioning. In open spaces, columns can help define areas without solid walls. Entrances and boundaries. Frequently used as gate posts or boundary markers. Design considerations. Load capacity. Must be designed to bear the intended load safely. Reinforcement may be necessary depending on the height and purpose. Foundation connection. Columns must be properly anchored to the foundation to avoid settlement or tilting. Weather resistance. Materials and mortar should be selected to withstand local environmental conditions. Aesthetics. Choice of brick color, pattern, bond. And column shape, round, square, fluted, can greatly affect the appearance. Advantages. Durability. Masonry is resistant to fire, pests, and weather. Low maintenance. Once built, brick or stone columns require minimal upkeep. Versatility. They can be customized to fit various architectural styles. Thermal mass helps regulate indoor temperature in passive solar designs. Challenges. Weight. Heavy materials require proper handling and support during construction. Cost. Natural stone and custom designs can be expensive. Labor-intensive. Skilled masons are required for quality construction. Conclusion. Brick and masonry columns combine functionality with timeless aesthetics. Whether for structural support or visual enhancement, they are a key element in many architectural designs. With proper planning and construction, these columns can last for decades, if not centuries. Columns based on shape and cross-section. Columns are vertical structural elements that transfer loads from the structure above to the foundation below. The shape and cross-section of a column play a crucial role in determining its strength, stability, and suitability for different types of construction. Columns can be classified into various types based on their cross-sectional shapes, which influence how they perform under loads and how they are constructed. 1. Rectangular or square columns. Description. These are the most common types of columns used in buildings. Applications. Widely used in residential and commercial buildings. Advantages. Easy to construct. Good resistance to bending in both directions. Limitations. Not as efficient as circular columns in resisting biaxial loads. 2. Circular columns. Description. These columns have a round cross-section. Applications. Frequently used in piles, aesthetic structures, and columns with architectural importance. Advantages. Uniform distribution of stress, more effective in resisting lateral loads, e.g., wind, earthquake. Limitations. Formwork is more complex and expensive. 3. L-shaped columns. Description. L-shaped columns are typically used at the corner of a framed structure. Applications. Common in boundary walls or corners of buildings. Advantages. Efficient use of space in corner areas. Limitations. Complex load behavior requires careful design. 4. T-shaped columns. Description. These columns resemble the shape of the letter T and are usually used in bridge piers or load-bearing walls. Applications. Structural supports in special architectural and civil structures. Advantages. Can support slabs or beams from one side. Limitations. Asymmetrical, leading to uneven load distribution. 5. I-shaped or H-shaped columns. Description. Often made of steel, these shapes resemble the letter I or H. Applications. Used in steel structures and large industrial buildings. Advantages. High strength-to-weight ratio, ideal for tall structures. Limitations. Not typically used in reinforced concrete construction. 6. Hexagonal and octagonal columns. Description. These have polygonal cross-sections. Applications. Used for aesthetic purposes in high-end buildings or monuments. Advantages. Visually appealing, symmetrical load distribution. Limitations. Complicated formwork, less common in regular construction. 7. Composite columns. Description. Combination of different materials, such as concrete encased in steel. Applications. Used in high-rise buildings for better strength and fire resistance. Advantages. Excellent structural capacity, durable. Limitations. Higher construction cost and complexity.